copy. Glad you can make it through the snow. So today we're talking about Poisson and geometric distribution. It's the last bit that you need to remember. Let's do on Thursday. On Friday, sorry. And then maybe you've seen an announcement that is with the Daily Digest and to a few other groups. But last semester I put out a poll about doing a session kind of introducing R. There's some interest, whether faculty in biology and psychology and other places, also within mathematics that don't necessarily do statistics, for some introduction to R. And I'm not doing a full pop-up course that requires more, actual quarter work of level of effort on everybody's part. But this is going to be 3 sessions that do kind of an introduction. Right? The first one would be, a few examples, how to get R in RStudio, how to install them, how to load in a few data sets. It would be largely a duplication of what you've seen, but it would review it. It would do a little bit more with a couple other data set formats, explain that a little bit more. So you're welcome to come. If you're interested, it'll just be in here and available. If not, there'll be integrity recording and a handout that'll get posted, and some links will be sent around that. And I'll probably link it directly from our class page, in case you're interested in that. The next 2 would, one would do a little bit more with manipulating data, a little bit of programming, I think with indices and things like that. And the last one would do a little bit more with packages or some other extensions. So just an introduction to get people going. It would augment what you have in the class. It's not required, certainly. As we use any of those things, eventually we'll do some simulations, so you will see some of that material as we go through the course. In that sense, the later 2 sections will be more of a preview of some stuff that's coming down the road. So if you're available and want to come, you're welcome to do it. Otherwise, we'll still give you the information. So homework 4 is due on Friday. It has a little bit of R code that can be used along with it. It has questions on binomial distributions and general discrete random variables, and then the stuff that we'll do today. But then after that, you should be able to finish it up. The material that's on R, and with the 3 classes, I don't remember how much you have to use that for this. But on the website for the class is this RScript command. Right? These R commands can do a lot of the computations for these different distributions and combinations and things that you need. So you can use those to check answers, to see how things go, to automate parts of it. On the homework, it'd be good to show formulas. So actually show n choose k, p to the k, 1 minus p to the n minus k. Or if the mean is n times p for binomial, show that formula, write down the numbers that go in. But in the end, you either can use your calculator or you can use R to get the numerical solution. Right? So if you take this RScript and download it, so if you save the link at some place, it isn't doing anything. It just pausing, I guess. Okay, there. It's going to ask me to save it someplace. Right? And you save it in some directory. Here, my R stuff, 140. Maybe I'll put it there. Computer's slow today. Maybe everybody's starting their computers in all the classrooms, or they're backing up something. But anyway, that should save. And then if you go to that directory, so my R stuff here is on my desktop or in there. And here's this thing. If I click on it, it just opened. I already had RStudio open, but it opened in here, and now it's a duplicate copy of that. But it just opened directly into RStudio and started it up. Right? And so what you would get with that is this RScript up here. And I saved this file, and I just put the RScript title in it, since it's an RScript. It has a .r ending, but I like to call it RScript. It's easier for me to find and locate my commands. So in 1b, it says calculate the binomial probabilities. Right? Here, the ones that have the comments are just comments. They don't necessarily do anything. These other ones do computation. So 0 to 5, if you just press run beside it, will give down here in the console window the number 0 through 5. And that's what it's doing, right? And so if you calculate the density of a binomial, size is what R calls our sample size in. That's just what it names it. And P is the probability. And you run that, and it gives you 4, or 5 probabilities, 6 probabilities. 0 for 5 is 6 numbers. So these are the probabilities you're going to want. Probability of 0, probability of 1, probability of 2. So if you use the binomial formula and check it on a calculator or check it here, there's ways to, choosing 3 out of 5, and then multiplying that 0.4 to the third times 1 minus 0.4 to squared. There's 5 of them, so 3 of one, 2 of the other. You get 0.2304, and that's this number here. So 0, 1, 2, 3. The probability that it's 3 is that number. This does all that calculation, right, for you. And so that will aid you in doing this, but do read the assignment, do write down formulas, annotate everything. You can either copy this and paste it into a Word document or something if you want to print it. Alternatively, you can just take these numbers and write them down. For most of this, there's not so many numbers, and it's not such complex output that you can't just write down the answers. Of course, you can copy it and put it into something and edit it, make it nice, however you like to do it. And so a few of these, go through there and will assist you. There's commands for Poisson, random variable, like the probability that you get a 0 is 0.165. That's one answer. But again, write down the formula, maybe double check that you can get it with your calculator, and so on. There's commands for geometric, that we'll go over today. And then there's a bigger data set with some frequencies. And as you graph probabilities, this is the graph you'll get of the different outcomes out of doing this. You can, just one graph that goes on the output. So you could just sketch that on your paper instead of copying and printing it. But if you want to copy this, there's ways to export it to an image or to a clipboard. You copy it to a clipboard, as a meta file or something. You can paste it into a Word or document that you want, as you like. That is where the R code fits into doing the homework. So it's an assist, really, for things. But any questions about that? Any big questions coming up on doing the homework, on any parts of it? We haven't covered Poisson and geometric, but on the beginning parts, are there questions on other ones about binomials? Yeah?
With 2A, are you basically just doing the same thing that you did in 1B? Because I did all that out and then I looked at the numbers that you get in R and I got very different numbers.
Very different numbers in calculating it there?
Yeah, like calculating out like the probability that like none of them and then the probability that one has it.
Yeah, so with that little probability.
Do you do the binomial formula with that problem?
Yes. It should be the binomial formula. So like what percent? So 4.14. Right? If the rate is 0.008. How many people did it say?
0 to 5 people.
5 people.
Positive.
Right. So for something like the chance that it's 2. Right, the general formula is n choose k or x e to the k, 1 minus p to the n minus k. So p is that.
Oh wait, I think that it's out of, it's 500 newborns and
Oh, I've got a 500.
Exactly 5 are positive.
Okay. Yep. So that exactly 5. Right. 1 minus p is 0.992. And so if you could write the numbers that would go into that. It's asking about, sometimes it's called x, sometimes it's called k, but it's 5 times out of 500. So putting it in there. In terms of calculating these things by hand, 500, choose 5, I can illustrate this one. The p 0.008. The fifth, because there's 5 that are yes, and 0.992, that leaves 495 that are no, right? And so you have to calculate that. Those are pretty big numbers for the calculator to handle. So maybe if it gets a little rounding error, it might be due to the huge number of things there.
For that one, do you not have to do all of the individual probabilities of like?
Let's see what it says exactly.
So would B be the one that you would have to do them all out?
Let's see. So in 4, right. So 500 newborns, what's the probability of exactly 5?
So you just have to do
You just have to do 5, exactly 5.
Oh, okay. But then for 4.15,
Yeah.
you'd have to do all of them out because it's at least 5.
So at least 5. You don't want to do 5 all the way to 500.
Well, yeah, you just do
You
0,
want to
1,
do
2, 3,
0,
4,
1,
5.
2, 3, and 4. So that's less than 5, right? So you can do those 4,
yeah.
right?
Okay.
Yeah, so it has you do those. And so for some of that, you could, like the 2B, you could write out the formulas. The R output gives those numbers. So you could, write out how the formula changes for that, and then fill in the numbers based on the stuff from R. But it's just trying to get some repetition to get the clear idea of using the formulas.
And then for that one, since it's at least 5, would you have to subtract your overall probability from 1?
Yeah. So if you calculate these 5 numbers, then add those probabilities together and take 1 minus.
Okay.
Yep. When you do the mean or standard deviation for these binomials, use the formulas for mean and variance. You don't have to go back to the more elaborate formula. For a binomial, the expected value is n times p, and the variance is n times p times 1 minus p. So that's a simpler command. You don't have to add up the individual probabilities all the way for that one. It would work if you did, but it'd be a lot of work to do it a long way. Any other questions? Okay, so we're going to introduce a couple new discrete random variables. There's a lot of different discrete random variables that are used in different cases. Some of it depends on the probability structure for sampling, other characteristics. And one that it has a lot of use in biology. Rates of disease, rates of immunization, rates of occurrences of different things, so on. So in terms of review, we're in this section of talking about discrete random variables. Right? We measure something, and we report a numerical outcome. In this case, it's a countable set, so we can list out the actual numbers. There's probabilities for each outcome. Sometimes we get those by a table or graph, or now we're getting some of them from formulas. Right? We can describe those distributions with the graph, the shape of it, the values that are most likely, but also mean and standard deviation. And for some of these special ones, we get special formulas like we use in binomial. Right? And so binomial, we got by having n trials or n cases. Each is success or failure, yes or no, is binary outcome. They're independent, they have the same probability p, and we count the number of successes. And if anything that we're studying fits that scenario, then it's binomial. And we can calculate the probabilities by the probability formula here. I can move this later carefully. And choose k, that combinatoric thing, p to the x, 1 minus p to the x. And then there were a couple of special versions for the mean and standard deviation. So we could get those quickly, and that describes where's the average value of this and how variable it is likely to be. Both the mean and variance go up with the sample size. As you get more trials, you get higher averages, you get more. Right? As the proportion of successes go up, you also get more. The variance is biggest near 1/2. If you get almost surely get success and p is really high, or you surely get failure and p is really low, then you concentrate on the end and there's lower variance. But if in the middle, you can go all of it, back and forth quickly. Now, other cases, we get something different. Right? A Poisson random variable measures the occurrence of a number of things in a fixed period of time or space or something like that. Right? And the occurrences typically come in one at a time, one person at a time, one occurrence at a time, one arrival at a time. And there's a parameter that governs that rate. It's called lambda in our book and some other books, right? And it's the rate at which things occur. And we're going to count the number of occurrences we get in that time period as 0, 1, 2, 3, etc. Technically, it goes on forever. You could have an infinite number. Most of the time, it's going to be in a restricted cases. The number of cases of measles that occur in a school district is going to be a small number out of the total. But this model, this probability structure, goes on forever. You would consider getting really big numbers in something like radioactive decay or other things where you really are dealing in the billions and billions of items that might happen. And this is the probability formula. The probability you get a number y is lambda to the y, e to the negative lambda over y factorial, where e is the exponential value, right? And so on the exam, when you use, if you're going to compute this, you're going to use your calculator. Most calculators have e, so you need e to a negative power. So the homework has you practice that. So check that you can get that e to the negative power, right? Just the mechanics of doing that. So here's one type of example that is done now. The National Council on Teaching Mathematics has yearbooks that cover different topics. In 1981, their yearbook was on statistics and probability. One example they had in there was about radioactive particles of a radioactive substance. So you have a kilogram of uranium, and in 7.5 seconds, you're counting, you have detectors around it, you're counting how many particles come out of it, right? And the rate could be 3.87 particles in that time period. 7.5 seconds, that's, double that is 15, and so 4 times, so it's 1/8 of a minute. I don't know why exactly they chose that time period, but it's 1/8 of a minute, and that's 7.5 seconds. Right. So, what's the chance we don't see any particles at all? Well, it's probably that it's 0. Our formula, in general, was lambda to the y. Now I'm using y here as the variable, e to the negative lambda over y factorial. 0 factorial is just 1. And lambda, whatever it is to the 0, is just 1, right, going into this one. So I'm left with this e to the negative 3.87 as the rate. So if you average 3.87 during that time period, the chance to see 0, according to this Poisson model, is 2.1%. So if you had 100 times that you're counting particles, 100 times of 3 seconds, right? You're doing it over and over and over again. The chance that out of those 100 times, but you'd probably expect about 2 times to get nothing. Not that common an occurrence. Probability that it's 1. Right? So lambda to the first, put a 1 here if you want. E to the negative 3, that doesn't change. 1 factorial is 1. And that calculates out to be about 0.08. And as you change the count that you're asking about, the probabilities change. So you get a squared or a cube for 2 or 3, 2 factorial, 3 factorial, down there, 3 factorial, right, is 3 times 2 times 1 is 6. So the divisor there is 6. And there's the probability. And so that's how you calculate the probabilities. Yes?
How is 0 factorial 1? Isn't anything times 0 just 0?
It would be, yeah. So they kind of make a special case that 0 factorial is 1 to put it in that sequence, and you use it in these formulas. Right? But if you get the logic, if you multiply that number down to 1, 0 kind of falls out of the whole system. So it gets a special definition. It works for all the other integers, but positive integers. So that's why I point out that one. So that's what you do. You keep going, right? It could go forever. Yes?
Could you just explain that exclamation point, just statement?
What this exclamation point thing is again? So so in this Poisson, distribution with our rate lambda. If this y random variable has this distribution, right? The probability that y equals one of these values is lambda to the y e to the negative lambda over y factorial. Right? And in general, y factorial is going to be y times y minus 1 times y minus 2 all the way down to 1. Right? So 8 factorial, well, let's do 7 factorial first. Right? It's 6 factorial, let's start easy. 5 factorial. Right? Down here. What are you doing? Okay. 5 times 4 times 3 times 2 times 1. Multiply those down there. Right? And that turns out to be 100. For 6 factorial, you multiply 6 times all of that stuff. So it's 720. 7 factorial, you get 7 times everything from before. So 7 times that, there's 4,900, there's 140, so it's 50. Right, 50, 40. And then 8 factorial is 8 times 7 times 6 times 5. Going on down. And so that's 40,320. The factorials increase pretty rapidly. They shoot off. After a while, the computer doesn't actually calculate them. It calculates things on a log scale because it can't handle it. Because 100 factorial is just too big to put in a computer. So, but where we got this factorial initially, as the introduction, is say we had 8 people that we're going to interview. Right? And we asked the question, how many ways are there to put them in order? 8 people, how many different ways can we choose to interview those people? The first person, the second person, the third person, right? So we have 8 spots. And you have 8 people to choose from that can go first, and then 7 are left over. And so you have 7, 6, 5, 4, 3, 2. At the end, there's only 1 person left. Right? And these type of choices where you get the choices for the first and second, you multiply them. So there's 40,320 possible orders to set up for. Yeah.
I just have a question going back to the problem we're just looking at. Is the lambda going to always be given to you, or is it the same value?
Lambda will change depending on the problem.
Okay, but that will be given to you. We don't have to calculate that.
Yes.
Okay.
Yeah. Typically in these, we'll give you that lambda.
Okay.
In some of these problems, right, what do I have as another example, right? So maybe that's on the handout. Right. In trials. Yeah, let's look at the handout. We'll see where some rates can come from for some of these, and then we'll come back just a bit. So one place where Poisson was used in the testing was in salt vaccine trials. They used another epidemiology, public health problems. And so there was one study, there was the placebo trial that had randomization. And there were 200,000 some children who were vaccinated, 201,000 that received the placebo, but were randomized to that. Out of this total, there were 57 children who had paralytic polio. And out of this placebo group, there's 142 who had paralytic polio. Right? So in these cases where it's a very large population and small numbers are relatively small numbers are occurring, the Poisson distribution used to model the occurrences or the chances. If you convert these numbers to rates per 100,000, you get a rate. So that could be your Poisson rate, 28 per 100,000, if they're vaccinated. So you could have here, so 28 per 100,000 with paralytic So if you had 10 million children, Poisson actually is really nice that as you clump it together, as you add more groups together, the rates add. The rate for 10 million, well, that's 100 times as much, 28. We'd expect about 2,800 children to have that rate. And a smaller example, let's say we had an area with 10,000 children. We would expect 2.8. So let's say imagine we have 10,000 children and our rate is 2.8. We can call that our rate or average rate, which we have these children have the polio. If that rate really applies to the children. Again, it's a pretty big group, small rates. So we can look at what's the probability that we get no children in 10,000 that have polio, or probability of 1, probability of 2, right, etc. We can calculate it according to the Poisson model. So for one child in the 10,000, right, our Poisson model would say that it's lambda, which is 2.8. Lambda the first, e to the negative lambda, right, over 1 factorial, which is just 1, or 2.8 times e to the negative 2.8. So if we figure out that probability, we would get the probability that we only have one child out of the 10,000 that have polio. In R, like there's a Poisson density function. So R kind of has you can do it by hand in R, or with the formula. So let me show you what that comes out to be. So exponential, that E function, there's an EXP or exponential function in R that gives that value. So the EXP of negative 2.8 is e to the negative lambda. Right? That's the same as 1 over e to the 2.8. That same value. So our probability of one child is then 2.8 times the exponential of negative 2.8. Or about 17% of the time we have one child out of 10,000. There's a density function for computing probabilities in Poisson. So we want, what's the chance of 1 when the rate is 2.8? And it's that probability. The chance of 2 children, right, 2 children. The formula says 2.8 squared times the exponential of negative 2.8. That doesn't change, right? Divided by 2 factorial. And I can't remember, but that's just 2. The density of Poisson, when you ask it what's the chance of getting 2, is that number. And now, how do you do factorial? I don't remember how to do factorials by themselves in, like you wanted, say you wanted 8 factorial. It has what's called a product function, 8. Right? So 1 through 8 gives the numbers, and product will multiply them together. I don't recall if there's another word. So when in doubt, R factorial, special functions of mathematics. It's called factorial. Right. When in doubt, Google it, and you can often get the help files for R to find a command. So factorial of 8 in R does that calculation. So factorials, let's say 18 is 10 to the 15th, right? It gets as it goes crazy. Of 28, it can't quite do it. Right? After about 28, the computer can't store it. They do it on a log scale because that I don't know, reduces the computation. So anyway, that was where a rate would come from, and another example of doing that. So where are we in the Poisson? The random variables, Poisson random variables have means and variances. it turns out, not surprisingly, I suppose, that the average value is just lambda. In this case, the variance is also lambda. It's kind of a special case. And so the standard deviation is square root of that. So if you expect 3.87 particles, the standard deviation is going to be square root of that, 1.97. So if you think about mean and standard deviation, mean going down a couple standard deviations, mean going up a couple standard deviations, you're likely to get, going down 2 standard deviations is about 0, so 0, 1, 2, 3, 4. Going up a couple standard deviations might take you up to about 8. So 0 to 8, 0 to 9 particles is what we're likely to get in this case. Now R also can generate random numbers with that distribution if you wanted to study anything related to performance of statistical. So there's a random Poisson. So say we wanted 10 numbers that had a certain Poisson distribution. And what was that, 3.87 in that one? Yes, right, about that. And so here's 10 numbers that came from a Poisson probabilities. 3, 4 are likely, 2 7s are there, that's kind of unusual. Here's another set of 10, here's another set of 10. And imagine these are different time periods and different number of radioactive particles are coming out. You're counting them. This is the type of thing that you would get. If you did, you do a bar plot of table, right? So if I do random Poisson and say I do this, what is that, 10,000 times. Right? These are my relative frequencies. Right? Sometimes you're going to get 0, 2, up to 8. Most of the outcomes are 0 to 8. The mean plus or minus a couple of standard deviations. But it is skewed. It can get a few bigger ones out there. But the probabilities are just above 0, going out to infinity. But they're so small, you're just not likely to see that. You probably have to do 1 billion times before you'd even get up to 20. So that's the Poisson distribution. That's the mean standard deviation. If you clump the Poisson together, the rate multiplies by how many things you put together. So if you do 10 times 75 seconds instead of 7.5, the rate is 10 times as much. And it turns out that these independent Poissons added together are still Poisson. So you can still use the same probability formula, but now with the new value of lambda. So the mean, variance, standard deviation. And for this longer time period, you can figure out kind of what is the range of likely number of particles you're going to see. You're doing that research. Well, here's some plots. 0 to 100, it really goes up to 1,000, but it's pretty. This was a rate of 38.7. The probabilities after a while start to look kind of bell-shaped. We'll talk about the central limit theorem. There's kind of an underlying phenomenon going on here, but it's not just by accident that it looks bell-shaped. It's something going on a little deeper. But focusing in on this area, these are the probabilities that you get from that Poisson probability formulas. This is random numbers that we talked about a little bit. And in the Salk vaccine trials, what they did in trying to decide, are we sure, can we really convince people and justify the expense and to immunize millions of children? Right? They did a statistical test, right? A hypothesis test. Are these rates the same, or are we absolutely sure that they're different? Right? They did the test here, and they did the test here. Now it turns out all of these seem pretty strikingly different. Twice as much, almost 2.5 times as much or so. In this one, it doesn't quite pass this 5% significance level test. The probability of getting, if it's average, if it's really 44, if it's average like that, the chance of getting 25 and 54 occurs a little more than 5% of the time. It's not completely surprising. It's unusual, but it's not completely surprising. Whereas getting 28 versus 71 is something that is not going to happen, 1 in 100 times. It's just very surprising. It's impossible to explain, or it's just very unlikely to explain by random chance. So you get convinced that really there is a benefit, and it looks like a huge benefit. So when this is the probability plots right, with a rate of 48, which is kind of an average of all those ones that we're seeing in the different studies. Right? And here are lines at 28 and 71. So if they were the same, the 28 and 71 really got separated out there where you have really low probabilities of having that. So we'll turn that, I think, gets turned into a p-value, or probability of getting something, a difference that big or bigger, just by random chance, and it's very unlikely, so it was strong enough evidence to justify the millions of dollars to spend. 54 and 44, for 20, 28, right? Those things are more, particularly the 54 is more in the middle, right? And so it wasn't so surprising just by chance. That's why the second study was really needed. But any questions? No. So for this one, there's some Poisson calculations. Sometimes you have to convert the rate to the local geography. So if it's rate per 200,000, you only have 100,000 people, you adjust the rate proportionally and you still do a Poisson calculation. Another random variable that we're going to look at is called geometric, all right, just as a different one. It's one that's useful. It's not too hard to do. It connects in with the probability, but it's something that we can figure out. Right? So the idea of a geometric random variable it has one parameter. It has its proportion p. And so we're going to do a series of trials. There's a certain bird called a cowbird. And this particular bird lays its eggs in the nests of other birds. So the other birds raise the offspring. And so this cowbird has a lot of eggs and distributes them around. And actually the species has lost the ability to raise its own children. But it's got better and better at sneaking the eggs into other nests that make it raise. So say you want to study these things. So we are going to check nests until we find one with a cowbird egg. And we are going to say, we're going to count, so how many nests did we make? If we have to search a long time, it's going to be expensive to try and go find these birds, right? But if we can go out and pretty rapidly find them in an area, right, it won't be such a hard task. And so we're going to have a series of trials. We're going to assume they're independent of one another, which might be a little questionable if there's a bunch of nests in one local area. But if they're spread out, it works better, right? And P is the probability of success. And our random variable X is the number of trials that we have to do to get a success. So what's the chance that, how do we write it here, that we do one trial on the same page? I'm acting up a little bit. So we're going to ask what's the chance you get one trial, two trials, three trials, and so on. What's the chance that you have one trial? And you find it on the first thing, the next equals 1. You look at one nest, what's the chance it's successful? Just P, right? Just the probability. What's the chance we have two trials? To have two trials, we have to have a failure and then a success. Yes?
2P?
No, not 2P. 2P would be doubling the probability of that one success, right?
1 minus p times p.
Yeah, 1 minus P times P. Right, so failure and then a success. Whereas this one has a success. Right? 3 trials until we find our first one.
1 p squared.
Yeah. So you gotta get 2. If these are independent, we multiply probabilities just like we did in the beginning probability, etc. So the probability that x equals k for k greater than or equal to 1, general formula is 1 minus p to the k minus 1 times p. We have k trials, and the first k minus 1 are failures, and then we get 1. Right? The same type of model gets used in some ways for respondents to a survey. How many people do we have to ask until we get somebody to respond to a survey? If response rates are 30% or 40%, well, you can figure that out. There's a generalization of this called negative binomial, which adds up a bunch of geometrics. So there's another one that comes out of this. If you want to get 300 people and the response rate is 30%, how many people do you have a budget to contact? In one survey that I've been involved with Departments of Veterans Affairs want to interview 42,000 veterans about their health care and their use of health care. And the response rate is about 30%. So they have to take 42,000 divided by the 30%. So they're asking more like 144,000 veterans to try and get 42,000. So that's a little more generalization of this, but that's what's going on. Right? So, right, that's how we get this variable. Here's the probability formula for that. Here I call it x equals 1, 2, 3, 4 trials, the number of attempts. It turns out that the expected value is 1 over p, so that you would expect to have to, 1 over, if there's a high proportion of success, if p is really high, like 90%, 1 over 90% is a pretty small number. You get your successes pretty quickly. But if something's really, really hard to do and really rare, like 1 in 100, and p is 1%, you probably have to expect to do 100 trials before getting that one special thing. So if you're searching for the planets, looking for one that could possibly support life, and it's 1 in 1,000, chance that you actually get something like that, right? You would expect to look at 1,000 before you find your first one. Could be having working. The variance has this formula. It's also going up with small values of p. Here is some plots of geometric probabilities. The geometric probabilities always go down as you go further. If p is higher it is, the more concentrated it is back on these values, and you have to wait a shorter period of time. As one example of this, right? There's a shop in near Quechee, Vermont, near Woodstock, in the southeast, kind of middle east Vermont, called Simon Pierce, where there's glass blowing. You're down there traveling. Have you ever been there? No. You just heard of it?
Yeah.
Yeah.
I live around there.
You live around there, right? So you can go there. They have a dining room. But you can also go down below and see them making the glass with the furnaces and blowing into the tubes and spinning the glass and cooling it and shaping it. There's also a swimming hole there, so in your swimming suit, jump in. But if the professionals, they're making these by hand. They're making sets of glass that people buy, wine glasses, water glasses, other decorative things. But they do make some errors. Is that sometimes it becomes imbalanced, or the wrong size, or it becomes too thin. So let's imagine that the chance of error is 1 out of 100, 1 out of 11, sorry. Or about 9% of the time they make an error. But they make them several in a row. We could ask, how many do they make before they typically have their first error? So the chance that error on the first time is just 1 out of 11. Right? The chance that if an error on their second time they make it using these formulas, 10 out of 11 would be the chance they make a good glass, and then an error is about 8%. And the third time, you multiply those two together, so it ends up like that. The chance that they make an error, the first error they make is on their 21st glass, right? They make 20 in a row that are good, and then make one error. It's about 1%, 1.35%. Right? So 20 good ones and then 1 bad one. So yeah, they could go potentially quite a long time before having one they have to recycle and melt again and spin. the expected number is 11. That their first error is expected to come in about 11 tries. Sometimes longer, sometimes smaller. The variance, the standard deviation is about 10.5. So it is pretty variable. Right? The mean is 11, the standard deviation is 10.5. So you can't quite do, the mean plus or minus, or particularly minus 2 standard deviations very meaningfully. It's skewed. There's a long right tail. Right? And you could use R to graph that distribution. So say our values of x go from 1 up to, say, 20. That little notation there gives me a vector or a list of 1 through 20. And let's see, is it geometric? And so, yes, so it does give the same probability that we do here. But x goes from 0, right? So they're counting the number of failures as the variable. So that's going to be a little bit different than what we have. With some of these random variables, there's just different ways that it can get represented. You can count the number of failures until a success, or the total number of trials, or they differ by 1. And so that's a little bit of a headache, but that's reality. The different books and sources do different things. So if we really want to graph this, right, the density of geometric, we're interested in really are 1 less than that. And if the rate of errors is 1 out of 11, we get these probabilities. I think these match what we had up there. So the probability of 1 and 2 and 3 and 4 and 5 and so on. So if we do a little plot of our values of x, 1 through 20, versus that thing, right, we get a plot. And our geometric probabilities are going down. Right? The average is 11. Or maybe we should do this a little bit before. Let's say x goes, not that, but from 1 up to, say, 50. By naming things, I can just run that same code again by just changing x and not have to change a bunch of that many numbers. But the probabilities gradually decrease. They really do decrease, but the plotting accuracy can't fully capture that. But it's decreasing. The average is about 11. But there's a non-trivial probability going out here that you have 20 or 30 times that these, they can make glasses without making an error. So if you had 2 employees, one had a rate of 1 out of 11, another one had 1 out of 20, one had 1 out of 5, right? You would have some evidence about how accurate they are in terms of making these glasses. Maybe you want to keep the one that gives a more success, less reuse. But maybe there's a training period that goes into that. But any questions about? So there's a couple problems that use geometric. Geometric looks a lot like binomial because there's independent trials, constant probability, but one has sample size, fixed sample size. You do in trials. Another one is counting until you get that. Right? So, but you get different random variables. So they get used for different things. Do you think the attempts at blowing the glass really are independent of one another?
No, because the more you do, the more experienced you are at glass blowing.
So for a lot of things like shooting free throws, doing something, maybe there's experience in learning and the probabilities change, or you fail a bunch of times, and then you pay attention and you really try to do it, and you change your probabilities and they're not independent. It's hard to know, but maybe if these people are professionals and there's not unusual circumstances like the beginning of the day or the end of the day, you kind of normal operations, they do it day in, day out, they do it the same way over and over again. Maybe for them it's more independent. Right? They aren't so psychologically affected if one is bad and another one's good in terms of how they do it. So, amateurs trying it though, who knows? There probably is a big learning curve. And then it's actually kind of a hard thing to determine whether probabilities are changing or things are dependent on one another. Like hot hand in basketball. Is it that somebody is success breeds more success, or is it that just somebody's performing at a better level? So it's actually kind of hard to distinguish those differences, but that could happen there. Okay, so that's what we have for today. Any questions about any of the distributions or the homework? Great. Zoe, previous one, and Matt. Matt here, no. I think we'll get the last homework back graded on Friday. The grader had medical school interviews, so she was out for a while. Yes. So is it next week? For the schedule, online, so for our class, does anybody remember exactly?
It's on the 20th.
It's on the 20th. So the 20th would be a week from, so it'll be this homework 4, 164, is the main core material. So Friday is reviewing. So there's a practice material posted, some study problems, but we'll talk about that more on Friday. And I think maybe Wednesday, Monday in class is a full review. Most of it will be memorized, but we'll kind of clearly say what it is. Like the binomial formula is one, calculating standard deviation.
Yeah.
Thank you. Thank you.
Have a good one.
Yep. Oh, yeah.
That's the coverage.
Okay, thank you. Great. And I'll send them an update list today.
Okay.
We can get more.
Great. Thank you.
Bye, have a nice day.
Yeah, you too.
See you.
Have a nice day.
Yep.
Thank you.
Yep.